Alrighty, we've got about like a little less than a minute till 7:30. Oh, it's literally 7:30 right now. So, yeah, welcome everybody. Happy Wednesday. It's the last day of classes. So at 7:30 p.m., which is right now, everyone should be completely done with the semester outside of just tests, just finals. So that's a little exciting. It feels good for me, and I know that much. So, of course, finals is always stressful, but it is just kind of nice just be like, whatever happens, I don't have to go back to class until February. So, I don't know. Um, but yeah, welcome. This is my last SI session of the semester. Gonna be probably the last one I'll see almost all of y'all, unless sadly you fail and have to see me again. I hope I don't have to see you again. Um, But yeah, it is that time. So a little sentimental. Yeah, F's in the chat. No kidding, Jason. But it is sentimental, and I'm gonna miss you guys. Y'all have been really, really awesome this semester. So yeah, my regulars, you know who you are. I'm gonna miss the crap out of y'all. I'm sad that I never got to see y'all in person. But and saying that if you ever see me in person, just walking on campus, feel free to say hello. I'm a pretty friendly guy and would definitely love to meet y'all. So, yeah. So, I'm not doing Chem 1308. No, I have locked in the 1307. I've really enjoyed it. Yeah, I know. Yeah, but y'all have one. I literally can never remember his name, but this one guy who teaches 1308, he's truly fantastic at it. Like, in my opinion, one of our best SI leaders that we have right now, and he teaches 1308. So y'all are going to be truly, truly in great hands. Can't wait to spam email for 1308 questions. Hey, I'm down for it. I really am, especially for my regulars, the ones that I know y'all's names. Like, y'all can really email me for anything, whether it's graduate school or anything like that, and I can definitely give you advice or just put you on your way. So, just because this is the last time you will be seeing me doesn't mean I'm not available in the future. So, yeah, I got you, Juliana. So yeah, and thank you all you guys for so much kind words throughout the semester. It has definitely made the job a lot more enjoyable. We don't get paid very much, and it is a lot of time or a lot of commitment at times. So the kind words do go a long way. But today yeah, exactly. That's how you qualify. Today, pretty much just gonna be like Monday. We're gonna do a little bit of independent work. I'll go over the answers, and we're gonna be done. Have I feel like today we should have absolutely plenty of time to go through the entire packet, as well as I only put enough questions where I feel like I can really take the time to fully explain every single answer. So it should be a really, really good day. Really good SI session as well. Let me go ahead and drop the packet one more time and the chat. We say that every time. Yeah, y'all do. Y'all do. But if you do open that here, I'm gonna go ahead and start sharing my screen. But I do have a review that is gonna be my review for I'm glad that it's kind of our inside joke, Jackson. But that review is going to be over. It's pretty much just my exam 1 review, my exam 2 review, my exam 3 review. And then yesterday and today, I worked on little stuff for chapters 11 and 12. I'm going to go ahead and just throw this out there to say my booty. It is obviously not exhaustive for every topic that is going to be tested. It's definitely got the bulk and what I would assume is going to be like the more trivial stuff that they could like trivialize is going to be on there. So I don't know, definitely anything that is on that packet or on my review sheet, 110%, I would know it pretty close to heart. So yeah. I appreciate you, Ruth, for not. But to quickly look at it, it's pretty. Oh, this is my full one. Then I won't pull it up. But this is the part that I added today. Was here's 11, and then starts with 12. Really, chapter 11 really isn't too scary. The only thing that's going to be difficult, or really like the hard thing to really learn. Yeah, Amelia, I'll get you in just a second once I send you all off. Yeah, I'll post it again. Um, the one really hard thing about chapter 11 is just those molecular orbitals, which is that thing kind of at the top of my screen right now. We're gonna have one example of it today. They're really not too difficult. Well, they're conceptually confusing, but as far as what you need to know for the test is really not complex, really. So that's kind of what we're gonna be focusing on today is just sorry. It's just kind of what you need to know for molecular orbitals for kind of getting the answer as well as far as determining the bond order or just whether something is paramagnetic or diamagnetic. So yeah. And then here at the bottom is mainly just some, again, more trivial type stuff. Definitely want to know like for your phase diagrams, definitely want to know like your triple point. That's pretty common. Definitely realize I had put this on here. Water's the major exception. I had kind of put here for our phase diagrams. Really the thing that if they're going to test you over it for water, they want you to basically notice that this line, this is for CO2, which is going to be the same for like almost every element, is different than this line for water, which is basically just saying for water, as we increase pressure, we are going more towards the liquid phase versus typically when we increase pressure, we go towards the solid phase. So that's really the main difference that they could trivialize and ask you for phase diagrams on the exam. So just kind of wanted to point that out because that typically does show up. So yeah, I got some more little charts down here. Definitely know this chart. This chart on the right is pretty much going to be your quick summary for chapter 12, at least for dipole, that kind of stuff. I would just really know this. Do you think the final will be math heavy? Um, I wouldn't say as math heavy as my packet is tonight, but I mean, about a third test is going to be exam 2, which is almost all math. So do with that what you want, but shouldn't be a ton. Should be a good bit, but not the entire thing. So hard money. If you, yeah, Macy, I'll drop it again. If you do not see the review pack or the packets literally right now being dropped in chat, please message Alan your email and he will send that to you through email. But with that, let's go ahead and get started. So again, I pretty much said we're going to have time to independently work, and then we were going to have me work afterwards. So this first page only has 5 questions. I want to give you like 7 minutes. I think 7 minutes is pretty doable. And yeah, I would start with the combustion analysis problem. I had the combustion analysis on my Monday packet. However, we didn't really get to it, and I explained at the end, but a lot of people had already left by then, so I just want to put it on here again. So yeah, so 7 minutes. Go ahead and try that. After 7 minutes, I will come back. If you have a question, feel free to either drop it in the all chat or put it in the private chat, whichever you are more comfy with, and I'll answer that. And yeah, good luck. We got about 1 minute left. It was the time. On a scale of 1 to 10, how hard was it? And also, was that enough time? I don't expect it to be enough time for all of you. Hopefully, at least some of y'all got through it all in 7 minutes. I understand the combustion analysis question can take a good bit. If you don't know really, if you're not super like versatile in it. So yeah. How many do we have to do? I wanted you to just do the first page. But if you didn't finish the first page, yeah, again, I had kind of assumed you may not get all the way to the bottom just because that combustion analysis traditionally is known to take quite a while. So 10 being hardest, about a 5, other than question 1. Okay, very fair. I think that's a very fair answer. You got through 2. I'd say honestly, if you got through the combustion analysis and the second one in 7 minutes, that's probably exactly how you should be pacing yourself for the final. Um, so you're good. But yeah, let's go ahead and go through it. Yeah, 1 was hard. I wanted to just start off with this just so everyone can see it. Just because everyone does need to know how to do it. You just need to know how. Okay, so let's read it. So 12.915 grams of a biochemical substance containing only carbon, hydrogen, and oxygen. I'm just going to stop there for a second. So someone had PM me asking, how do I set up this balanced chemical equation? And kind of my answer was just, well, really, we don't know the balanced chemical equation because we don't know what the biochemical substance is. That's our reactant. That's what we're trying to solve in throughout this problem. Is that we want to basically find out how much carbon was present, how much hydrogen, and how much oxygen was present. So they're saying that this thing made up of carbon, hydrogen, and oxygen was burned in an atmosphere of excess oxygen. So we know it's going to be CHO plus O2 forms CO2 plus H2O. And that's just because anytime we have a combustion reaction, it's always going to form CO2 and H2O. So quickly, we just know that those are going to be our two products, which is very, very key. Subsequent analysis of the gaseous results yielded 18.942 grams of carbon dioxide, so the CO2, and 7.749 grams of water. Again, that's how you should just know that it yields carbon dioxide and water, but it is very simply giving it to you here as well as it is giving you the masses. So I'm just going to go ahead and write those masses right here just so we are caught up with everything. 7.749 grams. Okay, cool. It says determine the empirical formula of the substance. Specifically, the substance is the biochemical substance. So basically, the whole process that we're going to be doing is we're going to be basically understanding that they want us here. I'm going to highlight this in blue, this in yellow, and this in red. They give us two masses for the carbon dioxide and the H2O. The key thing, all this hinges on you realizing that whatever amount of carbon that was initially present in the biochemical is present here because there is no other way carbon can leave. If it's burning up, it can only become carbon dioxide or water. So however much carbon is present in the carbon dioxide collected, that's how much carbon was present in the biochemical. Same thing here for our hydrogen. H2O or water is the only source of hydrogen. So we know that basically we can take however much weight of water was and basically just say, okay, well, water is 18 grams, and only 2 of those grams is hydrogen. And so basically using that proportionality towards the 7.749 grams, we can basically say, okay, like hydrogen's 1/8 of 7 grams, essentially is what we're going to be doing, which we're basically, so that will give us about 1 gram of hydrogen. And I just did that in my head. So we know that when we're working this, initially we should be getting that there was 1 gram of hydrogen initially present in the biochemical. So I know that is just very open-ended words, very just conceptual, just me exploring stuff at you and not really making sense. So let's see the actual written work of it. But again, I wanted to try to at least attempt to kind of give a little bit of preface. So again, we want to find the mass of each compound first, because again, to find the empirical formula, we must know moles, and the only way to get to moles is through grams. So the mass of our carbon, again, the only way we can get to carbon is through that CO2. So we're going to start with what is given, that 18.942 grams, 18.942 grams of CO2. I always start my stoichiometry over 1. And then from here, all we're going to do is just say that how many grams are in 1 mole of CO2. There's 44.01 grams of CO2 in 1 mole. And within one thing of CO2, 1 mole of CO2, there are how many moles of carbon? 1 mole of carbon. Exactly, excess, so sorry, Shelby, if I'm just not saying this. Excess oxygen does make it hard because there are 2 spots where oxygen can come through. Basically, what we're going to end up doing is that they gave us a total mass of the biochemical. If we know how much C weighs and how much H weighs, we can just subtract that from the total weight to give us oxygen. So that's kind of where we're going with that. So a good thing to be noticing. Okay, so now we're in moles of moles of carbon, because again, there is 1 carbon for every 1 CO2. So 1 mole of CO2 is 1 mole of carbon. And then from here, finally, to get into our grams of carbon, we do say that for every 1 mole of carbon, we do have 12.01 grams of carbon. Multiply that out, and I got there's 5.1694 grams of carbon in the CO2, which is therefore the amount of carbon present in the biochemical reactant. Okay, we're going to do this exact same thing for hydrogen. I'm going to kind of speed up the process a little because I think I explained it. So again, we're going to be taking the mass of water because it's the only source of our hydrogen. We're going to go ahead and convert that to our moles. So basically just dividing by the molecular weight of water. So we're basically saying that this 7 grams is about, 1/2 of a total mole. And then we're going to say for every 1 mole of water, we have 2 moles of H2O because, 2 moles of hydrogen because there is, of course, 2 hydrogen per 1 water. So for every 1 mole, we have 2 moles of hydrogen. And then, of course, to finish this off, we'll say for every 1 mole of hydrogen, we do have 1.01 grams of hydrogen, which again, I had said earlier should be coming out close to 1 gram, which I have as 0.867 grams of hydrogen, which is exactly what we'd expect, at least what I expected. Okay, so again, I had kind of prefaced it a second ago, but to find this mass of oxygen, we cannot use carbon, or we can't use carbon dioxide, and we can't use water because oxygen is present in both of them. So what we're going to do is we're going to take this 12.915, and I'm going to go ahead and just draw an arrow so that when we're going back, maybe looking at this a couple days later from now, you do know where I'm getting that 12.195. That is coming from, the total amount of biochemical. And what I'm going to do is just subtract what we know. We know that there was 5.1694 grams from the carbon, and we know there was also 0.867 grams from the hydrogen. When you subtract those 2 numbers from your total, this should give you the mass of oxygen that was initially present, which I find to be 6.879 grams of our oxygen. Okay, so that is that. We have officially found our masses of our carbon. This is each individual mass here. But again, what we want is these x's. We want to find the empirical formula. So what we're going to do now is just convert the masses into moles. That's as hard as it's going to be, really. So again, to find the moles of carbon, we all know how to do this. It's just taking our mass. If my pencil will work with me. our 5.1694 grams of our carbon. I always put everything over 1. And again, all we're doing is just converting this to moles. So we're just dividing by the molecular weight of a carbon, which I got to be 0.4304 moles of carbon. Okay, so we know there's supposedly 0.4304 moles of carbon initially present. That is probably literally true. There was that much. But we need to keep going. Again, we are trying to find the empirical formula, basically the simplest format, not how much was truly present. So next, again, we want to keep finding our moles. So for our moles of hydrogen, of course, we did start with that 0.866, 0.867 grams. And of course, we will just divide this by the molecular weight of our hydrogen for every 1 mole, which did give me 0.86 moles of hydrogen. Okay. Last bit is now just our moles of oxygen. Same process here, the 6.879 divided by its molecular weight, which is about 16 grams for every oxygen, for 1 singular oxygen, because we're not dealing with oxygen gas. And that gave me 0.4299 moles of oxygen. Okay, so now here is what I'm going to ask a question. This is how much moles was initially present, but the question is asking us to determine the empirical formula. What do I need? What is the last step to get me to empirical formula here?
Don't you have to divide by the smallest subscript?
Exactly, Michael. Yeah, very nice. So exactly, because these are not whole numbers and we want our empirical formula to have whole numbers, we will always divide by the smallest value, which in this case is going to be this 0.4299. From this, we get that the moles of oxygen is equal to just 1, because of course 0.42 or 0.43 divided by 0.43 is just 1. Now, if we were to go over to the carbon, same thing here. We're still going to divide by 0.4299, which is almost exactly 4.3. So even though this technically the math will come out to just slightly off 1, we can go ahead and say that this is equal to 1 mole of carbon. My pencil is really crapping out right now. Exactly, divide by the smallest. Everyone's good. Okay, and then last one is here. I'm gonna do this in red, and then we'll divide here. But of course, I'm gonna just read this as 0.04 or 0.43, just so it's a little bit easier, because this is 0.86. We can kind of quickly see that this is gonna end up being just 2. Oh. So now we have our empirical moles. Again, initially present was this 0.4304 moles, but in our empirical formula, we're basically saying that it's a 1:2:1 ratio, because we had 0.43 moles of carbon to every 0.86. So there's double the carbon double the hydrogen as there was the carbon to the 0.43 oxygen. So again, it's a 1:2:1 ratio, which is exactly what we're finding by dividing by the smallest, which therefore does give us that C1H2O1. Of course, you do not by any means have to put those little subscripts at the bottom, but it definitely does help. Just kind of keep everything in process. So that is combustion analysis. I went very slow on purpose, but does that help for if anyone was like really struggling with it? Does that kind of clear up maybe where some of the processes were coming from? Let me know. Yes? Okay, perfect. Got some PMs too.
Would we balance that at the end, or no?
No, not really. It's just looking for the empirical formula. So this would be the empirical formula. Yeah.
Okay.
So like when we answered it, we wouldn't have to put like that and then the product is CO2 plus H2O.
No. Yeah. So again, you totally could like balance the equation. CH2O2 plus O2 forms CO2 plus H2O, and then balance it to get the correct amount of oxygen and such. But again, that's the question isn't requiring that. It's just simply looking for the empirical formula, which is just that. So
Gotcha.
yeah, it's possible, but they didn't ask for it. Okay. And I got 1 PM asking why did we divide by the 0.4299? Divided by the 0.4299 is simply just a step that we must do for empirical formulas. Anytime it's literally the last step for any empirical equation. Is just if we aren't left with whole values, we must always divide by the smallest molar value, which in this case was just the 0.4299. So just because it's a rule. We didn't come out to all whole numbers. I therefore must divide every single molar value by the 0.4299. Okay. What does it say under 0.43043 moles C? 0.4299, I think is what this says. Yeah, 0.4299, this question, yep. So if it's close enough to 1, then we can just round up. Exactly, yeah. For this case right here, this was probably actually about like 0.0. Actually, it might have even been slightly larger than 1. It might have been like 1.01 or something like that. If it's within, like, I would even say like a 0.0, I would say within 0.1 even. If it was like, maybe not 0.1. I would say if it's like 0.93 and above, go ahead and say it's 1. If it's like 1.07 and below, I would go ahead and just say it's 1. If you get to like 1.1 or 1.15 or like 0.85 or 0.9, that's when I would kind of just go back and check and just make sure that you can just make that assumption. It should almost always come out very, very close, especially for an exam. But yeah, if you're getting values that are just close to 1, you're good to just say, okay, I'm close enough. Okay. Let's go ahead and move on. So wait, hold on, one more question. Wait, what if it's under 0.93, or they probably aren't going to do that to us? Yeah, if it's like 0.9, I would say that is probably close enough that I would start to get a little weary. But again, I don't think they would give you one, but I would just say with confidence, if it is like 0.95 or above, you can just say, okay, it's 1. It should be 1 at least. 0.93 though, I would start to get a little hesitant. But again, they shouldn't give you a case like that. It should generally be pretty clear. But if you got like 0.85 at that point, that needs to become a whole number. So yeah. Okay, so a gas mixture with a total pressure of 300 torr consists of equal masses of neon and argon. What is the partial pressure of argon in torr? Let's go ahead and just get some answers in chat, because I think this was a very doable one. And yeah, so what I want to do here is I just want to say, so it says that they're equal masses of neon. So I'm just going to go ahead and just assign a certain mass to both of them. I'm just going to go ahead and say that there's 40 grams of neon as well as 40 grams of argon. Just because it's saying equal masses, and I want to very accurately represent them. And one very important thing that kind of hinges on this problem, it goes back to a few exams ago, but there is 1 mole of a ideal gas, sorry, for every 22.4 liters at 1 atmosphere. So in saying that, as we double that, it quite literally is doubling and doubling. So in saying that, we're basing this off of moles. The amount of moles is representative of basically how much is actually present. Because if every single gas is 22.4 liters in 1 mole, if one thing has 2 moles and the other thing has 1 mole, we can say that makes up 66%. So why are both 40 and not just both 20? You could 100% use 20. I am just doing this just so that I can say that argon is just 1 mole, because it just says that the atomic weight of argon is 40. So I just went ahead and just used the larger mass, just so, yeah, you can take it out of 100 or whatever you want, but towards the end, you just want to get it to moles. So I just simply did that because I knew that 40 grams is exactly 1 mole of argon, and that because neon was 20 grams, I know that this is quickly 2 moles. So I know for equal masses of neon and argon, there is 2 moles of neon for every 1 mole of argon. And this is simply as much as we need to solve the problem. All we're going to do from here is just literally say, because moles is representative for how much percentage of pressure is going to be made up, we can literally just say that the partial pressure is going to be equal to 1/3, because specifically we're looking for an argon, and it is 1 mole out of the total 3 moles, because the 3 moles is coming from 2 moles plus 1 mole. So all we're doing here is just saying there's 1/3 of the total pressure is coming from argon. So 1/3 times the torr is equal to the total partial pressure of argon, which is just 100 torr. So again, it's just, all this is doing is just finding the moles and just doing a mole fraction times your total pressure. The word masses always gets me really confused. Yeah, this problem is a very, very easy one to either flip and solve for neon, or like say argon had 2 moles or had divided or multiplied by 2/3. So yeah, it's very easy to flip these one backwards. That's why I like to just start with setting 40 grams to 40 grams and then just saying, okay, this is 2 moles. And if this is 2 moles, I know it's got to make up, 2/3 of the total pressure, which is 200 torr, which makes the other one 100 torr. So just keep looking at the molar equivalents. So why did you not just use 40 and 20 and say the argon was 200 torr? Because it specifically says that there are equal masses of neon and argon. So if I said that one was 40 grams, the other was 20 grams, then we would end up saying that there's 1 mole of each. And if there was 1 mole of each, then we'd have 150 torr for each. Sorry, yeah, I PM. So in case someone was confused who I was talking to. But okay, so that is that. And that I think this is a pretty fair game difficulty level to be up on your exam as well. So if you kind of stumbled on that one, just kind of pay attention to the wording. And yeah. All right. I like this one a lot. Let's get some answers in chat. What do we think? In which process is the delta H, the change in enthalpy, equal to the change in E, the change in energy? So we got 1B, we got 1C, we got 2 C's, a third C, fourth. Okay, we're pulling away. So this equation that you need to know with this is pressure and volume, basically in terms of gases. So the main thing to be noting is that, well, really, this is the hard part, is realizing that you need to apply this equation. But whenever delta H is equal to delta E, that means that we have a 0 change in our volume and our pressure. And so when we're going through these, we just want to read the cases in which there's no change in volume or pressure. So sodium carbonate is heated. Okay, anytime we see a change in heat, that is going to change literally everything about us, specifically our volume in this case. So I'm going to say here, heated, change in temp is a change in volume. If I have a soda can and I make that soda can extremely hot, we understand that it's going to expand. So that's a change in volume. So just from that, this does not have a delta, this delta H is not equal to delta E here, because again, we have a change in volume. Don't even need to read the last of this. 2 moles of ammonium gas are cooled. Again, this is another change in temperature. So I'm just going to kind of draw an up sign. If we have a change in temperature, we have a change in volume. C is going to be our answer, so I will go ahead and highlight it. 2 moles of hydrogen iodide gas react to form hydrogen gas and iodide gas in a 40-liter container. Nowhere there does it say that we're changing pressure. We end up going to having equal moles on each side because of how our stoichiometry is going to come out to be, or sorry, our balanced chemical equation. So there's no change in pressure. So pretty good there. You may not be certain yet, but you want to continue to read. 1 gram of water is vaporized at 100 degrees Celsius, and at 1 atmosphere vaporized is going from a liquid to a gas. We understand that is a very, here, liquid to a gas. That is going to be a pressure change, huge pressure change. We understand that gases have way less pressure pushed on them than a liquid or a solid does. Last one is 1 mole of solid carbon dioxide sublimes. That is going straight from, again, the solid to, I believe it's solid into a gas. Yeah, it is solid gas. Haha, I have it written on here. Solid to a gas, which of course is another change in our pressure. So there's that. Okay, I don't think probably not too many questions because I kind of wrote why for what. This last one is going to be a limiting reactant problem. Go ahead and drop in chat what you got. I'm going to read it really quickly. So it says aluminum oxide. It gives us our formula. They give us a weight of aluminum as well as its molecular weight, as well as they give us a weight for oxygen and its molecular weight. And they're basically saying what mass of aluminum oxide can be formed. What we're going to do with this is take our 2 masses given for our aluminum and for our oxygen, run them to completion, and basically just say which one made the least. And whichever one made the least is the limiting reactant, and therefore how much is going to be produced in reality. So I'm going to start with just this 82.49. Again, we're just going to run this this aluminum to completion really quickly. I always put everything over 1. From here, we have, it gives it to us 26.98 grams of aluminum for every 1 mole of aluminum. From here, we want to go straight into our mole to mole ratio because, of course, we are trying to find our grams of our product. So we have to say for every 4 moles of aluminum, there are 2 moles of our aluminum oxide. And then again, that is coming straight from our balanced chemical equation. And then once we're in moles, of course, everyone starts to see that when we want to go from moles to grams, it's really as simple as just multiplying by the molecular weight, which is 101.96 grams of aluminum oxide, which in this case gave me 155.9 grams. I will go ahead and say, because everyone pretty much said in the chat, this is going to be our limiting reactant, but I am going to quickly write the other one out for those that want to see it, but I'm going to write it a little bit quicker. But again, same thing. If you didn't know, obviously, right off the bat, which you shouldn't know right off the bat, which is the limiting reactant, you want to run this one as well. Same process, starting with how much oxygen is initially present. Go ahead and getting it into moles. That way, once we're in moles, we can go from a mole ratio of our reactant to our mole ratio for our product, which in this case is our aluminum oxide. And once we're in moles of aluminum oxide, we know that we can go ahead and convert that very quickly into our grams of aluminum oxide using the exact same weight as before, which in this case gave me 249.9 grams. So of course, in this case, 159 is going to be the limiting reactant. And I will just kind of write over here that Al is limiting reactant. You can pretty much guarantee limiting reactant is going to be on your exam. So if you are still struggling with limiting reactants, do kind of brush up. But again, the whole point is just to run your 2 masses to completion. These aren't hard equations. They literally give these to you at the beginning of the year because they want you to understand stoichiometry. It's not a problem they want you to trip up on. They literally just want to see if you can run a stoichiometry problem from the reactant side to the product side. That's really all it is. So if you get freaked out with that kind of stuff, just don't. It's really just see if you know how to put fractions and multiply them. Okay, it is 8:10. I don't know why I was so excited to say 8:10, but I was. But yeah, I'm gonna give y'all probably 7 minutes on this page as well. I think y'all will probably I'm gonna give y'all 6 minutes actually, just for the sake of time. I think y'all will probably get through every single problem on this time. 8:10 is cash money apparently. But I will give y'all 6 minutes on this. I think y'all will get through all these. Yeah, I don't have much more to say, but one thing I do want to say is the first page was chapter 2. This page is chapter 3, and the next page is going to be chapters 11 and 12. Just so you know where we're at in the grand scheme of things. So 6 minutes on the clock, as per usual. If you have questions, drop them in the all chat or the private chat. Either way is good with me. So good luck. You got about 3 minutes left. One minute. Sorry. That is the time. So go ahead and stop if you want to stop. I guess I can't stop you, I guess. Can't stop you from not stopping, but it is the time. So how was that? Let me know on a scale of 1 to 10, with 10 being the hardest. Let me know. I expect not hard. From what I hear, y'all did pretty phenom on exam 3 tests. So yeah. I would say, yeah, I didn't expect this to be too hard. Just to kind of preface, I obviously did put 3 questions for electron and molecular geometry. Still know that stuff 100%. They're going to have some questions on it. Know the difference. Well, I don't know. I guess I don't need to be prefacing this, but do you know the difference between formal charge and oxidation number? Stuff like that. We'll be going through a few more specifics as we do go through. Let's go ahead and jump into it, y'all. So write the full set of quantum numbers for the outermost electron in GA. I don't remember the exact name. I feel like that is gallium. I'm not positive though. Pretty sure it's gallium. Let's go ahead and just start it off. So let me go ahead and just ask here. Let me go and write NL, imps of L, and imps of S specifically is what I'm going to be looking for. I'm going to go ahead and ask y'all in chat, what is the N value? And while you're typing that, how can we find the N value? Very nice, y'all. It is going to be 4. And where do you look for that? How'd you know that so quickly, y'all? Yep, exactly. It's going to be your period number, specifically like 4A. Don't count to like 1, 2, 3, 4, but 4A more specifically. So if you do go to 4A, oh, wait. Sorry, period, not period, not group. I was looking at group number. Sorry. 1, 2, 3, 4. Period number 4. 1, 2, 3, 4. Of course, is going to be our gallium here, right here. Going back, however, it is relevant on which side of it is relevant which group it is in, because based on which group it is in determines which block it is in, which in this case, of course, this is going to be in our P block. I had me worried for a second too, Lauren, don't worry. So in saying that, what is going to be our L, because we are in the P orbital. Very nice. Yep, it is going to be a 1. If you have forgotten our S for our L's, L is equal to S is equal to 1, P is equal, or sorry, S is equal to 0, P is equal to 1, SPD is equal to 2, SPDF is equal to 3, and then after that it does go alphabetical as well as just continuing up in the L value. So you could have F, G, H, I, continuing from 4, 5, 6. Cool. Imps of L, what does our values of imps of L always range from? Okay, perfect. Yeah, we're getting in chat. It's going to be -1 to 0 to 1. Yeah, it's pretty much as simple as that. It's all your imps of L is always going to range from the negative L to the positive L. Yeah. And then the imps of S, in this case, what do y'all have for your imps of S? Plus half or minus half? Yep. So I guess you could say plus or minus half, but I am going to say that it should be plus half. Specifically, we'll look why. It's just by convention. Technically, like, no one can tell you you're wrong if you say a negative half. But because when we are filling in our molecular orbitals, we do by just convention for our P. This is going to be our 4P here. By convention, it is just 1 electron into the P orbital. So it is just simply just a 1 up arrow. We do associate the 1 up arrow with just a positive half. And so just by convention, we always put up arrows to start. We therefore, by convention, are saying that the 1p electron is going to be a positive half. So I'm going to say positive half. Cool. So hopefully that kind of makes sense for that. But yeah, I think y'all are doing pretty good on that. Is L2? L is always going to be from, or no, L should be 1 because we're going to start at 0 for S. So like S is 0, P is going to be equal to 1. So yep, no problem. All right, moving on. Which element in group 4A has the smallest radii? Very nice. It is going to be our boy carbon. And the trend, we do get larger and in size as we go down to the left. So typically we say that helium is going to be your smallest element, and that I believe it is tungsten the name? No, tungsten is not the name. Francium we consider to be our largest. So that's going to be your most bottom left is going to be your largest. So just from that, you can see that. Of course, our 4A, carbon is going to be the highest up. So there you go. How many valence electrons does, I believe it's just titanium or Ti have? What do we have in chat? We have 3, 4, 2, 2, 2, 4, 2, 4. I'm going to go ahead and say it is just going to be 2. So let's go ahead and just look at it for a second on the periodic table. Let me look at her. Very cool. So we do have Ti is just going to be here. So we are going to have a, let me draw it over here more specifically. If we were going to do its condensed electron configuration, we will have argon, and then it will be 4s2, 3d2. So our valence electrons is always just going to be the amount of electrons in our highest principal quantum number. So I'm going to write valence E equals number electrons in highest. I'm going to say N, which N, of course, is principal quantum number. And this right here is the N, as this is the L. Okay. So because 4 is higher than 3, we will only count the 4. If this was 4s2, 3d10, 4p6 or 4p4, then our valence electrons would be 6. And just while I'm talking about it, if we were to go to 4p4, 4p4 would be selenium, and we understand that selenium has 6 electrons. or 6 valence electrons, because we understand that we're getting 2 electrons from our s, and then these 4 are the remaining 6. Especially from, like, I think carbon is a really easy example. We understand that carbon has 4 valence electrons, and that is because it's coming from the first 2 s's and the 2 electrons from the 2p. Again, those transition metals, because we are dropping down a principal quantum number to fill those orbitals, those are not considered part of our valence electrons. So there will only be 2 valence electrons, even though there are 4 electrons present in like this condensed electron configuration. We only count the highest principal quantum number electrons. Okay. Oh, you're looking at TI and group 3A? I see. Yeah, if you did that, then oh yeah, there is another one right there. Yeah, if you did that, then I would say that has 3 valence electrons. So for the people who put 3, then you're definitely right with that one. Okay, moving on. So is the 2 from the D or the S? The 2 is from the S. The highest principal quantum number is designated by that just the number. So the 4, because it is higher than 3, 8 is the valence electron. So the 2 valence electrons comes from the S orbital. Okay. Which of the following sublevels is filled last, y'all? Go ahead and drop it in the chat. I'm going to go ahead and just rearrange these in how we would find them in real life. So we have 4s, 3d, 4p, 5s, 4d. This is how we would read the periodic table. We know that as we're going across the 4s, suddenly we do hit transition metals, which do drop us down to that 3d. We jump back up to a 4p when we go back, continue across the period. Same thing, 5s, once we go to transition metals, we drop down to the 4d. Therefore, the 4d must be filled last. Sorry for that must being so loud. It was at least loud on my end. But yeah, the 4d is going to be filled last because, again, it's just the most furthest on the periodic table. So, yeah. Alrighty, in the following structure, give the formal charge and the oxidation number of oxygen. So I'm going to write Fc as well as ox number. And then we'll work this. Go ahead and type in chat, what do we have for our formal charge and our oxidation numbers respectively? I'm going to go ahead and work it, and then I'm going to explain it. Okay, cool. Everyone is doing it right. It is going to be +1 and then -2. Oxidation number, you should really never be missing. Isn't the 5, hold on, I have a PM. Isn't the 5s higher in energy than 4d though? So the 5s would be filled last. No, sorry, unfortunately, if we were to go to the 5s specifically right here, 1, 2, 3, 4, 5. Strontium is going to be 5s2, but after we go to these two, we understand that when we're going from strontium, like that, of course, is a complete 5s, but the next thing is going to be 4d, and we can never even start to fill these orbitals until we've at least had those 2 electrons in the 5s. That's why it is simply filled last, is because we literally can't ever put an electron here until we finish that 5s orbital, because just simply by how the periodic table is set up. So hopefully that makes a little bit more sense. Okay. Hold on. I'm going back, don't worry. Okay. I couldn't tell the bonds by the picture. Can you show how it is 6 for formal charge? So formal charge is a +1. But don't worry, I'll go through the math of it. One thing that I do want to note is that oxidation number you should really never be getting wrong. Oxidation number is almost always, should be for this class, always what you expect in the periodic table. So oxygen, we literally understand that like fluorine is a -1, oxygen is a 2-, nitrogen is a 3-. That's our oxidation number. What are the formulas? Don't worry, I'm about to get to that. So just from that, oxidation number you should just literally be getting. Okay, so oxidation number, this is, here, I'll quickly write it. This is going to be your valence electrons minus your unshared plus your shared. However, for oxidation number, while this is the formula, the very key thing to be understanding from oxidation number is that your more electronegative atom always receives all of the shared electrons. And so because there is, 2, 4, 6 electrons here that are shared, that would It is 6 shared electrons. However, there are 0 shared electrons for hydrogen. For as far as formal charge would, or oxidation number. Sorry, because if we want to do the ox number for hydrogen, it would be 1 for the valence electrons minus the shared. There's 0 shared plus, or sorry, there's 0 unshared plus the shared. But again, for oxidation number, the shared electrons always go to the more electronegative, which in this case is oxygen. So in this case, for hydrogen, it would also have 0 unshared versus oxygen here has 6 shared because it's more electronegative. For formal charge, this is still just the valence electrons, but this is going to be still this is unpaired, or I think I'm going to say lone pairs more specifically. Lone electrons plus half the shared. And for formal charge, the shared is the same across the board. It's always just going to be half the shared. Is this the dots and sticks equation? Yep, exactly. The formal charge is going to be valence electrons minus sticks plus dots. That's the easy way that I like to do the formal charge. Because if you do that, you understand that there's 6 valence electrons for oxygen, and then the sticks is just going to be 1, 2, 3 sticks plus the dots, and there's 1, 2 dots here. So 6 minus 3 plus 2 is equal to, just a plus 1. So that's how you can get it there. So yeah. Hopefully we got that. Let me know. Let me read the chat for a second. Is oxidation number always supposed to equal the charge of the elements, the charge of element by any chance? Yeah, well, oxidation number is always what is expected. Oxidation number is the amount of electrons wanted to be gained or lost to reach a noble gas. So for example, oxygen would like to gain 2 more electrons to become a noble gas, so it's a 2 minus. Fluorine only wants to gain 1 electron to become like a noble gas, so it's F minus. Let's see, lithium is a 1 plus, because it wants to lose 1 electron to become a noble gas. So that's how we always can see oxidation number through just the periodic table. Don't double bonds count once? Because I can't tell how you got 6 shared. No, double bonds. So double bond is consisted of 4 electrons, and so we're not really counting bonds. We're just counting amounts of electrons. So for that reason, a double bond is always going to have 4 shared electrons. And specifically, there is 6 shared because there are the 2 bonds. So there's 2 electrons in this bond, 2 electrons in this bond, and 2 electrons in this bond. So that's why I've been saying 6 shared. Hopefully that makes sense. Cool. Let me know if you got more questions while maybe we are typing some questions. Oh, okay, when does it count once then? I'm getting things mixed up. Good question. So specifically, if you don't want to do half times the shared, that's when I would just do the sticks plus dots. The sticks plus dots, you don't have to multiply by half. That's when you just count the sticks. For example, a double bond is 2 sticks. So like that's why this is like 3 plus 2 for oxygen, because we have a double bond is 2 sticks literally drawn, and the single bond is 1. So that's why I say 3 sticks. The 3 sticks are representative. The 3 sticks are representative of the half times 6, because there are 6 electrons for the 3 bonds, but we're multiplying that by half, so we're getting back to just 3. That's why I just say you can just count the sticks, because we're getting 2 electrons per thing just divided by 2. So that's why I just like to say just count the sticks for formal charge. Got it? Perfect. Okay, cool. This next one, let's go ahead and just get some answers in chat. What do we think about this one? This is, again, very trivial, but definitely important concept to be realizing for this next one right here. Let's get some answers in chat. It is going to be C. Very nice. Yep. The principal quantum number, which is just M, is associated with size, while the angular momentum quantum number, which is L, is associated with shape. And we know that like an L of 0 is the s orbital, which is going to be just a sphere. An L of 1 is going to be the p orbital, which we know is a dumbbell. An L of 2 is going to be your d block, which has like, I believe, 8 lobes. And then an L of 3, that shape is just literally just called complex. Principal quantum number, that is, we increase principal quantum number as we go down, correct? And we understand that as we go down down the periodic table, we're also getting larger and larger and larger in molecules. So same thing here. That's why it relates to size, because as we go down the periodic table, our principal quantum number is getting larger. Yeah. Momentum is m sub l, exactly. Yes, and then spin is just m sub s. One thing I do want to note that these are actually just backwards. The principal quantum number is associated with the period number, and the angular momentum is associated with the blocks. So those would just be flipped, would be the correct one. What was m sub s? M sub s is just the spin. It's just, that's the physical quantity, is just spin. So, okay. I'm going to go ahead, well, maybe a few more questions could be trickling in. I'm just going to go ahead and write electron and molecular here so that we can quickly fire off some of these answers, and I can just say yes or no and be good. So for this first one, we have over here this compound. What do we have for our electron and then for our molecular geometry? So we're getting a lot of T-shape. T-shape is definitely going to be the molecular formula. There we go, we're getting it now. And the electron geometry is going to be that trigonal bipyramidal. And kind of the way to see this is that this this part right here is actually going to, here, let me erase this overlapping circle. This kind of middle part right here is going to be kind of the linear planar part, and then these kind of coming out are what's going to kind of make that, sorry, that 3D is so literally so bad, but that is what's going to actually make that trigonal planar. If I can maybe try to draw a little bit skinnier here, it would kind of come up like this would be one of the fluorines, and oh, that is so bad. And this would be the other fluorine. We can say that this is to the electron pairs, and here's another fluorine. As we can see, hopefully you can visualize, these are going to be about 90 degrees to each other, which is literally just forming a T. So hopefully that kind of conceptually, I don't know, visually helps if to try to draw that. It is, no, it's not seesaw. It is going to be T-shaped. Sorry, if I said seesaw, maybe because in a second we're about to see seesaw. It is T-shaped though. Yeah, I get molecular, but electron. So electron is always just going to be based on the amount of electron groups. So here we have 1, 2, 3, 4, 5 electron groups, which is representative of how I was kind of drawing it a second ago. We have one group here, one group here, one group here. We're going to have one group here at the top of the pyramid, and then of course one group here also at the bottom of the pyramid, making that trigonal bipyramidal. Sorry. Hopefully that kind of visually helps. But yeah, I do have let me, in a second I can try to pull up a link that I really recommend for looking at this stuff too. But I'm going to go ahead and say this next one, I will go ahead and say is also trigonal planar. As you can see, it has the exact same amount of electron groups. We still see that there is the 1, 2, 3, 4, 5 electron groups. So still have that 3 in the middle, that planar part, and then 1 on either end of that, creating that pyramid on the top and pyramid on the bottom. What is going to be the molecular shape for this SF4? Seesaw, yeah. So I do want to point this out because I think seesaw and T-shape are very easy to get confused. But do just literally notice that T-shape is just quite literally a true T. I think it's easy to see that seesaw a seesaw, but I think when we see the T shape here, we think it's seesaw just because it literally is like kind of like on that little the little pivot is what I'm looking for. But here, I feel like this picture does a really, really good job of kind of showing you kind of like this part is kind of the more seesaw part, and that bottom is kind of like the legs. It's kind of seesawing. So again, just try to keep those two differentiated in your head. That seesaw is going to have 4 molecules versus T-shaped is just going to have the 3 molecules versus they both have 5 electron groups. Okay. Again, there is going to be a chart in my review sheet that really just goes over that very clearly. Okay. Last one, electron and molecular geometries for H2O. What do we have for our electron geometry? I'll go ahead and tell you that for H2O, here, I'll draw it because I'm a nice guy. There are 4 electron groups here. Exactly. 4 electron groups is representative of a tetrahedral. And then what about our molecular shape? Very nice. Yep, it is just going to be bent. Again, if you're having trouble with that, that is just memorization. I truly, truly recommend just going and staring at that chart for a while. And then let me see if I can. Oh, I don't have the link anymore. I thought I still had the link on my notes app that I could just quickly share with y'all. But okay, we are getting low on time. We have 20 minutes left. So in saying that, I'm gonna give y'all. Yep, here, let me. Well, I don't have the chart pulled up. Give me a second. I don't know if I'm. Oh, there we go. Yep, this chart. This is the chart I was talking about. It should be on the exam review. So, yep, recommend doing that. Okay, for this, I'm gonna give y'all 6 minutes. If you haven't seen molecular orbitals yet, or like really understood how to like work with them yet, I would just kind of skip that one and just let me explain it, because I think I'm just gonna kind of give you what you need to know to do it. And yeah, and then we'll be done. So I'm gonna give you like 6 minutes, maybe 5 minutes. Probably stop y'all like 5.5-ish. I'm gonna stop talking so y'all get the most time now. But I'm gonna go ahead and put 6 minutes. I may stop a little early, but again, if you have questions, feel free to drop them in the all chat or the private chat. One last thing, your time is ticking. But if you have questions on any of this, I understand that the final is literally like less than a week now for y'all. If you have questions or just feel like you didn't want to ask something right now in the SI session, you can seriously, like truly, please do not hesitate to reach out and just email me. I promise you, if at times I seem scatterbrained on email, everything is always going to be very far more organized. So if you just want further clarification on anything ever, literally just shoot me an email, and I promise you I will get back to you with a truly like concise, clear answer. So I don't know if anyone has that or needs that, but again, if you need further clarification ever, please just email me. But okay, good luck. Okay, sorry, I know y'all are working, but I am right. Oh, sorry, Sarah, I just sent that to you in PM. I am right now dropping in the all chat a link to the link that I was wanting to give you all a second ago. It's just a website where you can go and just build molecules as you want them, add as many elements or electron pairs as you want, but it lets you like turn everything in 3 dimensions to kind of like truly see the shape, and it's like super easy to just like take away an element and see how that changes the overall shape. So definitely recommend that link that I put in there. Just mess around with it. It truly will help you conceptualize molecular and electron geometry. So Okie dokie. That was the last timer for the semester. So kind of surreal a little for me. Feels kind of good. I know, stop. I know, we're coming to an end. Yeah. Um, yeah. Have a good night to the person who PM'd me. Okay. Let's go ahead. Just reset it. Let's do it again. No, we have to get through this. It is sad though. It is sad. Y'all been really awesome, but let's go ahead and get through this because I know a lot of y'all are here too for the packet. So, how many grams are in 5.5 grams of carbon? Stop. Y'all are too sweet. Thank you, Ralph. Of course, I really just wanted to do this one just to kind of remind you that atoms is associated with Avogadro's number. This specific question isn't associated with chapters 11 and 12. But when I was making the packet, I was like, let me throw this in there just to make sure we know. Very nice, Jonathan. And that is exactly what I'm getting. So let's kind of go through that. So we have 5.5 grams. We want to get into atoms. The way that we get there is converting grams to moles and the moles to atoms through Avogadro's number. So in saying that, we're going to start with always what we're given. And then we want to get to moles. So we're going to divide by the molecular weight of carbon, just 12 grams, to get to 1 mole of carbon. From here, last step is that we just say for every 1 mole of carbon, there are 6.022 times 10 to the 23rd atoms of carbon. We could have also called that formula units or molecules. And we would still multiply by 6.072. Yeah, exactly. I got exactly, oh, this shouldn't be a times, this should be an equal sign. Yep, I got exactly 2.76 times 10 to the 23rd carbon atoms. Very cool. Okay, let's look at this next one. Let's try to do it kind of quick like, yeah. So this is, what is the bond order F2 plus? Use the molecular orbital diagram below to aid you. First thing that I'm just gonna say, oh, very nice. Okay, I guess we're more comfortable than I thought we were going to be because we do have 2 correct answers in chat. But the bond order, I will say, is that it's going to be the bonding electrons minus your antibonding divided by 2. And while at first this may seem like very scary, it's really, really not too much. If you thought it, well, if you got 1 or 2, you probably added or took away too many electrons, and we're about to see that. Basically, what we're going to do here is I put fluorine. Okay, so first off, we have F2 plus, which means that just there's 1 less electron than there typically is. So this left, what's happening here is this left side is basically the bonding orbitals of 1 fluorine, and this right side is the other bonding orbitals of the other fluorine. I have just by convention gone ahead and just said that this right side fluorine is the one that lost an electron, just so that we know when they combine, it still keeps that positive charge. What we're going to do is the first step is that we're just going to fill in these left and right sides with the molecular orbitals that we've been doing in the past. So in the past, we had said that fluorine has 7 valence electrons, because if we were to go to your periodic table, we have 7 valence electrons. You add an electron instead of subtracting. Exactly. That's what I figured happened. Okay. So, but yeah, from here we do see that fluorine is right there, leading us to the reason that it has 7 valence electrons, because group 7A. And so from that, when we're filling in our 2s, we want to continue to do up, down, fill in the orbitals. So this is literally what we've been doing in the past. We have 1, 2, 3, 4, 5, and then go back to match 6, 7. Again, nothing new, literally just doing the molecular orbitals like we have been doing. For this F plus, of course, we're going to have 1 less electron. So this is going to have 6 valence electrons. So I'm going to have 1, 2, 3, 4, 5, and then 6. Okay, we're halfway there. Now, all this is very complex and has a lot of conceptualness to it. The first thing I do want to point out that anytime we have a star is equal to anti-bonding orbitals. Anti-bonding is basically just saying that there is another orbital or a region of space that isn't currently occupied with electrons, isn't occupied with bonding electrons more specifically. That's really all that anti-bonding is. There is a true definition in the review sheet, but we're not here really to get into that. what we're here for is filling this out. Really, the simplest way that I can explain this is just add up the number of electrons that will be present here is the number of electrons present on each side of your valence electron. So for example, we have 7 valence here and 6 valence here. So we know that total there is going to only be 13 valence in the middle because this was equal to our 7 plus our 6. It's going to be now what we're going to do is literally follow the exact process. I see. Yeah, I figured you might have added 2 more, but super easy to do. But we're going to pretty much follow the same process as filling the molecular orbitals as we just did. We know that the middle is going to have 13 electrons because that's the max amount of valence electrons present. And what we're going to do is just going to go up, down. That's 1, 2, 3, 4, 5, 6. When we get to p's, we're going to continue with the up, 1 up to each before we match them. So 2, 4, 6, 7, 8, 9, 10, 11, 12, 13. We're done filling out the molecular orbitals. This is it. We see that there is nothing currently in the sigma 2p antibonding orbital, and that the pi 2p antibonding orbital is unpaired. These aren't super relevant to the problem, but it is just important to note. So now we're pretty much done. Again, the bonding orbital to solve, it's just the bonding orbital is antibond or bonding minus antibonding. I had already said that antibonding is anything with a star. So we can literally, I'm just going to go ahead and highlight for case of simplicity. Yellow is going to be our antibonding, and our blue is going to be just our normal bonding. And so from this, we see that we have 2, 4, 6, 8 bonding minus our antibonding, which is 2, 4, 5. So 8 minus 5 divided by 2 will be giving you 3 divided by 2, which is equal to 1.5. So there it is. And I have pretty much good confidence that they're going to be giving you a question on your test asking you for the bonding orbital value. So that's how you do it. Again, the left side, do your traditional electron configuration stuff. Once you're to the middle, all you do is just count up how many electrons you were used and just continue with those rules that you've done in the past. Go from bottom, lowest energy, up towards the highest energy, matching them as after you've had one unpaired. And then once you've done that, just go back and just look at what's antibonding, what's bonding. Can you repeat the last part again with the bonding orbital? Yep. So just from, it wants us to use the molecular orbital diagram to find the bond order. The bond order is, the equation is just the bonding electrons minus the anti-bonding electrons. And these are going to be represented with these stars. So we see here that this has a star and this has a star. So we have 1, 2, 3, 4, 5 anti-bonding. So I have 5 here for the anti-bonding and 8 for the bonding electrons represented by the blue, which is 2, 4, 6, 8. So 8 minus 5, and then divided by 2 is just part of the equation, which got me to 1.5. Why would you give one side the F plus? I just did that just because it's F2 plus, so we understand that somewhere along the way they lost an electron, and so just by convention, I just went ahead and just said that it was one side, just so that we can see that one of these, one of them basically one of them will have the opportunity to form 2 bonds, but the other one wouldn't. So that's why I assigned just one of them F plus, just because in reality, even though they're together when they have a cation charge, in reality, one of them initially lost an electron. So I'm just representing it as just one side, just to be the most accurate. Will we get the diagram on the test? Yeah, you should, almost certainly. One of the imposter, yeah, pretty much, a little bit. Will there be like 2 problems like this in the final? I could see that. I would at least 1. I wouldn't think much more than that though. 2 max, maybe 3 max, probably 2 max though. It depends on how they're feeling. Okay, go ahead and drop answers in the chat for this next one. I'm gonna go ahead and finish writing. I know a lot of y'all do want to just kind of see the structures of these, so I am going to write these really quick. Like I've already started them, but put in chat, what do we think the answer is going to be here? Okay, pretty nice. Everyone is getting C, which is going to be the answer. And that is because which three elements can hydrogen bond with? So I'm gonna go ahead and just highlight this as well. Yep, fawn. I'm gonna say NOF, NOF, because if it's not F, O, or N, it's not a NOF. So yeah, it's not a NOF. So you know it has to be NOF, NOF, because if it's not NOF, it's not a NOF. So yeah, that's how I remember it. But yeah, so nitrogen, oxygen, and fluorine, it has to be attached to those. So in saying that as well, you can pretty much see here that this first one, it does have fluorine, but these hydrogens aren't going to bond to the fluorine because fluorine not only is already bonded to carbon, but every single one of those hydrogens is already bonded to a carbon. The only case that we see and through these examples, right here, we have a hydrogen finally bonded to an oxygen, as well as the oxygen does have lone pairs to allow for additional bonding of a hydrogen. So that's going to be the hydrogen bonding. Okay. One really quickly, I would like to say that if you are having questions on bonding, there is a good bit of bonding stuff on this or on my review sheet. I'm not exactly sure where, but I'm not going to take too much longer. I can't see it right now, so I'm not going to worry about it. But there is some good stuff on dipole, that kind of stuff on there. You do need to know that as well. All right, next one, which is true concerning the dipole moment of the CO2 molecule. Let me go ahead and draw this while this is it. So it's kind of giving it away. But what do we have as our answer? It is B. Yeah, it kind of just is contingent on you drawing out the molecule. To quickly do it, just because we have 2 minutes left. CO2 has 16 valence electrons. So when I did this, I would have just gone oxygen to carbon to start, which then leaves me with 12 lone pairs, or 12 lone electrons specifically, because 4 of those are used in a single bond. So then I would have gone 2, 4, 6, 8, 10, 12. Okay, great. Everything's got 8 electrons, or does it? Because you see here, oxygen doesn't get the octet. It needs 2 more bonds. So therefore, we'll bring 2 lone pairs in, which therefore gives us C double bonded to O double bonded. Sorry, I'm drawing this wrong. This should be oxygen, this should be carbon, this should be oxygen. Because CO2. Oxygen double bonded is carbon, which is double bonded to oxygen. And of course, both those oxygen do have lone pairs. From that, you should be seeing it's linear, and which case B is the answer. Dipole moment is non-zero. That is not true because it's being pulled in both ways. It is a net zero dipole. Which is B. C says the dipole moment is 0 because the carbon to oxygen bond is nonpolar. That is just not true. It is technically it's not a nonpolar bond. It is a polar bond, and there's 2 polar bonds in opposite directions, making it nonpolar. D, the dipole moment is 0 because the molecule is bent. We see the molecule is linear, so it's not bent. And E, the dipole moment is non-zero because the molecule is bent. Again, it's not bent, it's linear. So cool. Okay, next one, which of the following is most soluble in water? You're gonna have, this is gonna be on your exam. They're gonna have this, something very similar. We got 2 D's and 1 E. The answer is E. To quickly draw these out, I'm not gonna draw out hexane, but hexane, ethane, and benzene are all just going to be this type of stuff. Going on and on and on. Carbon tetrachloride would just be C to Cl 4 times. And then KNO3 would look kind of crazy. Honestly, I don't even technically know how it would look. I bet it would look something like this, though. I would think it would look something like that. But from this, you should be seeing that these are all, hold on. These are non-polar, basically saying that there is no net dipole, versus in KNO3, we do see just from the oxygen alone, that because one has a double bond and one has a single bond, there's going to be a net distribution of electrons to one oxygen compared to the net distribution of an oxygen to another one. And so in saying that, this is going to be the only one that is that is polar. These are all over here non-polar. And water is polar. What we need to say from this is that like dissolves like. And so when you're doing these, because water is polar, you just want to look for the polar compound, which is going to be the salt in all cases. The salt is always going to have polarity to it. So in that case, yeah. How should we have known K though? You should have, just by convention, just by process of elimination, you should have been able to see that hexane, ethane, and benzene are all hydrocarbons, which are nonpolar, and that CCl4 is nonpolar. And so just because those are nonpolar, none of those are going to be, well, I guess that's most soluble, but you should notice those are nonpolar, and that potassium nitrate is just going to be polar, not only from how the oxygens are bonded, but also that it's a salt, and polar is going to be the best at dissolving itself, another polar compound. So hopefully that answers it. It says like dissolves like. Exactly, yeah. I know that's probably super ugly handwriting, but it is also, I believe, the very last thing on my packet or my review sheet. Like dissolves like. Polar. Oh, this should say polar dissolves polar, not polar dissolves non-polar. At least this one's right. Hopefully people will understand that was supposed to say polar dissolves polar. Because use this at all if you're stuck on a solubility question. Solubility is almost always dealing with salts anyways. We almost always have a cation with an anion, with a cation with an anion. So I would say probably no, just because they're all going to be technically like non-polar substances, because like KCl always going to have like a net dipole. Any diatomic element or any molecule that has more than just one, how do I say this? Anything that is not to itself is always going to have a dipole, because there's always going to be pooling. And so for like the solubility rules, we almost always had like KF plus like, I don't know, NaCl. Same thing here, like Cl would be the dipole. So just for that, solubility rules, we almost always have polar compounds to start out with. So yeah. Okay, cool. Last one, neon atoms are attracted to each other by blank. Last problem of the semester, and it's an easy one. It is going to be C, kind of a trick question though. Dispersion forces are going to be present in all molecules, all compounds ever. So for your noble gases, unless it's specifically like xenon with fluorine, in which that case would be like an probably like a dipole-induced dipole, because xenon doesn't normally have that. But in saying that, almost the only attraction that noble gases have is dispersion forces. Your dipole to dipole is going to be like, well, a dipole to a dipole, for example, like HF to HF. Like there's a dipole towards the fluorine, in which then that dipole would come end to end of another dipole. Hydrogen bonding, we understand, is hydrogen with an N, O, or an F. It has to be N off. Covalent bond is just a covalent bond, and then ionic bonds is just going to be an ionic bond. That's going to be a charge to a charge. Again, that all that good stuff is going to be in my packet. Here it is. Here is some dipole, hydrogen stuff. One thing I do want to note about it is that please do try to learn your energies. The energies is going to tell you your relative strength of things. So for example, like your ion dipole is your strongest because it requires 440 to 600 I believe kilojoules. Yep, kilojoules per mole of energy to break it. So yeah. So the most soluble would be the one with the greatest net dipole movement. That was a PM. It depends. I would say the most soluble is always going to be the one. If we're given a polar compound, we're asking which most soluble. Always look for the one that is polar. But if we're comparing polar to polar, I would typically start to look at those intermolecular forces. So like if we did have like or ion dipole, that would make it more soluble just because it's going to have a stronger intermolecular force to each other. So hopefully I answered your question. Your question was kind of abstract, but I hope I somewhere in there answered it. But maybe rephrase your question if I didn't answer it. Perfect. Okay. Yeah, the finals 50 questions, 2.5 hours. Y'all have literally got it. Here, I'll drop the Insta. I could always use some Insta follows. If you want to follow me on Instagram, it is Creighton_G. That is also my Snapchat. If you would like to, for some reason, add me on Snapchat, I'll add you back. I probably won't Snapchat you, but you can see my stories if you want. Can I go over the questions? Do you mean just like go back through them? Because I can definitely do that.
Yeah, just go back through them if you don't mind.
Yeah, for sure. I got you. But yeah, it's the end of the semester for me, guys. It's been really fun. It really has been. Yeah, Jackson, we can start straight for sure. It's been a really, really fun semester. Y'all, again, I've tutored I've been the 1308 SI leader, and while I did enjoy that class, y'all have really been awesome. Like, y'all have been really very kind to me. Very, very kind to me. Y'all have really showed up and showed out. Y'all have really made me look good to my boss. Like, I don't know why y'all chose me, but y'all did, and I'm thankful. I know that I do put in the time, but it is really, really awesome to have so many people coming to me every week and just really saying so much nice things. So I know that some of y'all think that I did some crazy amount to help y'all get a grade, but in reality, I can only lead a horse to water. I give these sessions whether there's one person or a million people. So do take pride in your work. And yeah, thank y'all for coming every single week. I literally know some of y'all literally came to every single session, and that's literally mind blowing. Like, it really is really, really cool. So one last easy money. I don't know what to say it to. Today, I don't know. This exam for y'all is gonna be easy money. If you came to this session and you're working hard, it is easy money all day, every day. Next Tuesday or Wednesday, whichever day it is for y'all, you've got it. You're about to crush it. It's easy. Have confidence in yourself. I've said it in a past exam. Going into a test with a negative mindset will only ever make you do worse. The worst thing you can do for yourself is go into an exam scared. So have faith, study hard, and you have one last battle. Give it your freaking all, people. Because afterwards you can sit back and say, I gave it my all. And you can have peace with that. I have had a few classes in the past where I didn't give it my all and it bit me in the butt. And I regret it literally all the time. Literally, I regret it all the time for the classes I haven't made A's in. So don't be that person. Give it everything. Can I reconsider Thursday night? It's locked in already, unfortunately. Oh yeah, I'll keep scrolling the pages for sure. Easy money shirts inbound. Oh my gosh. That would be kind of iconic, actually. Thank you, George. I'm assuming I'm saying your name right. That's very sweet of you to even remember that I played for that, but thank you. It means a lot. Creighton merch. I wish that would be cool. Yeah, thank you, Hunter. I appreciate you all. Thank y'all for staying as long as y'all did. I hope tonight's packet was good. Please do know everything on that review sheet. Have a good night, Alan. Thank you for staying longer than you needed to. I appreciate you a lot, and have a good finals week to you as well, Alan. Good luck. Yeah, if you're heading out right now, thank y'all. Have a good semester. Study hard. Study that review sheet. It's again not exhaustive, but it's got a dang good bit. Do you know how much of the final will cover chapters 11 and 12? I would only really say about like 10% of the question, or I would say about 15%. Out of 50 questions, I would probably think you would get like 5 to 7 questions. Thank you, Anne. I appreciate it. So yeah, love you guys. Thank you again all for the kind words, for real. But one last battle, y'all. Y'all may not be religious. I am religious. I truly will be praying for you. I 100% believe in manifesting your future. I don't believe I'm anyone super crazy smart or just anything super out of the ordinary, but I, through daily life, just tell myself that I am good at stuff and that I can do it. And it's gotten me all the way here. Again, I am no different than you are. So really, whatever you hold in your head and truly believe is going to be the outcome. So if you don't believe in manifestation, do try it seriously. If you tell the universe that you're going to do good, you're going to do good. So manifest this whole week. Seriously, I'm manifesting for y'all to do good. I really, really, really am pulling for y'all. So y'all are all going to 13 away. Exactly. I should not see any of y'all next semester. I will be mad. Thank you, Sawyer. Have a good night. Yeah. So I don't know, but thank you, Ruth. Yeah, to my regulars, for real, like, really thank you. I don't have words. I'm almost tearing up, but I'm not going to. Like, really, I really appreciate y'all. I'm someone who has had a very tough beginning of my life. My parents have kind of made things easy for me as far as like financially, but I've never been someone who people have just generally treated well. And so to come and talk in front of 100 people and everyone to be literally so nice and all the time and just so like what I assume is non-judgmental is really, 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 truly refreshing. While I am here to do a job, just having people who are kind and generous to me, it means more than you know. So can we give you any evaluations? Yeah, there is an evaluation. I'm pretty sure you got it through email. I think it's like closing like today or tomorrow. If you don't do it, it's not a big deal. But if you want to leave me a good eval, go for it. It does make me look good. I won't get fired whether you crap on me or not. So do be honest. But yeah. Yeah, I'm gonna tearing up a little bit too, Lauren. It's just I really appreciate y'all, probably more than y'all. Like I know I just keep saying it, but yeah, I really do have an impact on me, just like I have an impact on y'all. So good night, Joshua. Thank you. Can I teach? I wish. If I don't become a surgeon, I'm gonna be a chem professor. I've set that in stone pretty much. So yeah, it feels really weird to be kind of saying I'm about to end the session, but it's kind of that time, y'all. So I'm gonna miss y'all. What kind of surgeon? I want to be an orthopedic surgeon, so someone who does surgery on like broken arms and bones. I actually shattered my ulna and my radius in 8th grade. I've had like 3 surgeries on it, and so just kind of through that, I've become very interested. But to quickly summarize why I wanted to do that, but yeah, I did want to be an orthopedic surgeon. If that doesn't work out, because it's a very hard thing to become, professor is a backup. So yeah. Any physical therapist? No, not really. Just the surgery. It's very intensive surgery. I just don't want to ever be bored. Do it, Jackson. I can guarantee you my broken arm is probably just as gruesome. It was literally like a Z after it happened. It was crazy. Really, yeah. I mean, this scar is honestly pretty massive. Like literally pretty much spans my whole, you can kind of see it really well now. It pretty much spans my whole entire forearm. It's to the point where like I literally wear long sleeve shirts almost every day because I think it's so noticeable and I'm like very self-conscious about it. But yeah, it's kind of cool. You want to go to surgeon too? You've got it. Not ready for that much schooling. Yeah, and the MCAT. You've got it. Just take a step by step. The first step is just getting good grades in undergraduate. For real. Your tibia was sticking out? Okay, yeah. If you had bones sticking out, then you're on a little different page than I was. I didn't have anything sticking out. But that stuff is very cool to me. So yeah. Well, it wasn't happy. I'm assuming Lauren's saying it. But yeah, it's cool. If you ever have questions on like getting into med school or anything like that, I mean, I've done it. I literally am graduating next semester. Woo! But yeah, for real. If y'all ever have questions about like literally anything undergraduate wise or anything, if you're ever just confused with life, I've definitely gone through it and then some. So I think I'm a pretty good person to offer advice at times. So where are you gonna go to school? I have literally no clue yet. Can we say hi to Nick? I think he may be on the phone with his dad. I'll see. Hold on. My boss is emailing me. Let me go see if we can hear. Let me take you on my room is actually a mess. So I'm not gonna take you on a room tour. But we can say one last goodbye to Nick if he's ready. Bebe? You're on the phone? Oh, my kids want to say bye to you.
Bye, Nick. Bye.
Jackson said bye.
Bye.
See ya.
Bye.
He's so sweet. Sorry, he's on the phone with his best friend, but yeah, he's such a sweetie. I cooked potato soup tonight, but he finished it, so that was really sweet. So that's why he came in earlier. But yeah, that is the Nick. That is the goodbye. Jackson, good to see you officially.
No. Did you see my Christmas sweater today?
I did actually see your Christmas sweater. I don't pay attention a lot in that class, but I did see your Christmas sweater. It's pretty good. Wish more people would have done it, but it's good.
No, it was amazing.
But yeah,
You're gonna have to end it.
I know it feels weird. It feels weird. But yeah, I guess I am just gonna end it. So again, guys, I appreciate the heck out of y'all. It's been a fun ride. Good luck. Again, praying for y'all. Y'all got it. Go crush it and make yourself proud. Make me proud. We should all do Among Us. Literally, Ruth. Literally. I'm 100% down. Get that going. You're on it. You're in charge. But yeah, I would love to actually, that sounds like it's kind of fun to kind of like see some of you guys again in the future. But yeah, maybe we can do that in the future. Maybe we can do some Among Us with SIs. Among Us with your SI later. But yeah. I'm gonna give like literally 10 seconds for people to drop emails if they want to Ruth or private message her. But I'll add y'all back. Don't worry. I'll follow everyone back on Instagram as well. I just haven't got on my phone yet. But yeah, stay in contact. Again, my regulars, you know, I really will do just about anything for you. So yeah, if you ever need me, hit me up. I'm in your corner. And yes, Jackson, you are a regular for sure. For sure. I know your name definitely by heart. So yeah. Yeah, Juliana, I don't even know if I'm saying your name right this long this semester. But yeah.
You are saying it right.
Nice. Okay.
Yeah, people usually say like weird names too, like Wyliana or Juliana, but you're saying it really good. Yeah.
I'm like notoriously bad with names, so glad I got through the whole semester with that. But yeah, I'm gonna end it. So one last deuces, because that's somehow what I've always ended up saying bye with. But deuces, everybody. I think Nick just said deuces as well. So yeah, good luck.
Bye. Good luck. Take care.
Thank you. You too. Nick says good luck to you as well. So official deuces. Bye, y'all.